So yeah, hello everyone. We're going to present on our work for Team NotYourRL. I want to thank all the team members that are not here, especially so Alexander Fries, Alexander Sully, and Daniel del Castillo. And this talk will be split in two halves. So in the first one, I will give you a high-level overview over the sort of the theory and motivation of what we did. And then in the second half, June will take you through the nuts and bolts and the experimental details of our implementation. So first, the high-level approach, we oriented ourselves along the paper Reward Learning from Human Preferences and Demonstrations in Atari, which can be seen as combining two previous strands of research, namely deep Q learning from demonstrations and reward learning from human preferences, which we will now look at in more detail. So first off, deep Q learning from demonstrations. I'm going to assume that everyone here is familiar with the standard deep Q learning with experience replay algorithm. So then the main additional contribution of DQFD is to have an additional replay buffer of human demonstrations that never gets overwritten as training progresses. That ensures that over the course of the whole training, the agent will always have access to some high quality samples in its replay buffer. And then the loss that is used for training is split in these three parts, where the first two are standard reinforcement learning losses, so a double Q learning loss and an n-step TD error to deal with sparse rewards and longer horizon dependencies. And then the third term is new, which is an expert classification loss and is only applied to samples from the human replay buffer. It basically ensures that actions that are taken by the expert will receive a higher Q value than actions that are not taken by the expert. Now, having this loss is all nice and well, but we have a big problem, namely that we need a reward signal, which we do not have in this competition. And that is where learning from human preferences comes in. So the idea here is that we want to learn a reward model that takes in the current state of the environment or an observation like an image and predicts the reward for the current time step. And then we want to train this reward model by collecting preference feedback. That is, we generate clips by running the policy and then pass those clips to a human evaluator and ask for a preference over those two clips. So we set that all up, but in the end, we did not have enough time to actually test and especially test multiple runs of our human feedback gathering. So what we ended up doing instead was to use simple heuristics to generate auto labels. And our heuristics were that human demonstrations were always going to be better than the ones generated by the model, which in turn would be better than random policy trajectories. Additionally, given that all of those the tasks in question basically resulted in a completion at the end, we assumed that clips from later into the trajectory would be preferred to clips from earlier in the trajectory. Now, how would we actually train that reward model? It's a very simple approach. Given some network, for example, that takes an observation and predicts the reward, we just sum up the reward for every frame in the respective clip. So the clips here are labeled with sigma 1 and sigma 2. And then we pass that through a two-way softmax to get our probability that one clip is preferred over the other. And then this is scored according to the cross entropy with respect to the auto-labeled generated process. Now that we have our two building blocks, we can put them together. First, we have a pre-training step in which we basically just focus on this expert classification loss, which amounts to imitation learning in essence. So this results in an initial Q network Q0. Once we have that, we can go to the iterative part of the process, which is seen here on the right. Given our current Q network, we can generate, using the induced policy, can generate new trajectories. and feed that into our clip database and run our auto-labeling process. This can then be used to train the next iteration of our reward model, which in turn can be used together with DQFD to refine our current Q function.
All right, thanks, Tom. So from here, I'll take over to just go through how things went in terms of development, some experiments we tried, as well as the final results we got. So first, I'll show you a bit of the tooling that we built up in order to help out with development. So we built two custom tools here. The first one that I'll show you is the MineRL Trajectory Viewer, which allows us to explore the human demonstration trajectories. And then the other one will be the human preferences user interface, which we use to collect human feedback. So here, I'll just show you briefly. It's essentially a viewer that allows us to look at the demonstration data. So for example, you can see on the left side of the screen, you're able to see things like the actions over time and the rewards over time, which for this particular trajectory is empty since Basalt has no rewards. And then on the right-hand side, you're able to get like a good overview of like all the actions and the states and the next state information for the particular frame that we are currently viewing. And then obviously you're also able to scrub through the different frames throughout this trajectory in order to get a good idea of what's going on in any given point of the trajectory. So that's the trajectory viewer. And then the next one is basically we built this human preferences user interface, which is designed to collect human feedback, as Tom was explaining previously. So given two different clips collected from our trajectories, we want to be able to allow the human judge to decide whether the which clip is preferred. So here we have the two clips side by side. The human is able to play the videos to watch the performance of the agents, and then they can click near the bottom whether they prefer the left clip or the right clip. And then this preference will just get recorded into our annotation buffer, and then the interface will just pull out a new pair of unlabeled clips from the buffer in order to collect more feedback information. But as we mentioned, we are actually we didn't end up using the human feedback in our final submission, but we ended up using auto labels. So we found that this interface was also very helpful to help us debug and visualize what's going on in terms of auto labeling and our reward model. So if you just see right below the two videos, there's a box for the true label, which is essentially the ground truth we get from the auto labeling, telling us which clip is preferred. And then below those boxes, you see the prediction from the reward model, which tells you what's the predicted reward and the probability of either clip being the preferred one. All right, so now I'll talk a bit about our reward model. So first of all, once we finish the implementation of our workflow of training the reward model and we were ready to test, we didn't go straight into the MineRL tasks. We decided to just do a quick sanity check on a simpler environment. So here I'll draw your attention to the image on the upper right, where basically we have our testing on the cart poll environment. So we tested basically being able to learn the reward model for cart poll from pixels. And then we also ended up training an agent which was able to solve the cart poll environment based on this learned reward signal. So with that confidence, we basically were feeling good about going into the MineRL environments, and that's where basically we use the auto labels first to produce that data set. So you'll see that we generated 100,000 early versus late pairs of preferences and 100,000 random action versus human demonstration pairs. And these pairs, the full 200,000 were produced for each environment, and we use these in order to train our reward model. So how did the results go? We found that the reward model was actually quite proficient at predicting the preferred clip, and across all four environments, we've managed to get over 80% accuracy for the preference prediction. However, we did not actually see improvements in agent behavior when we trained the agent with this learned reward signal. And So unfortunately, based on this finding, we actually decided not to include the reward model part of the workflow in our final submission, though we do believe that this could be a promising approach, and hopefully with more time, we would look into potential problems. For example, we suspect that there might be issues in terms of the auto label quality, which is just giving us a reward signal, which is not very useful for the final tasks. All right, so with that decision, we essentially simplify our workflow a lot. So this is the algorithm that Tom was explaining previously. And then after we remove the reward model, we actually just remove the second part of this workflow. And then what we're left with is essentially just an agent that is trained via imitation learning on the expert human demonstrations. All right, so here I'm going to just briefly touch on some things about action shaping. I think there should be nothing super surprising about what we did here, but basically we started with this large action space presented to the agent from the BASALT tasks, where we get over 5,000 discrete actions, 2 continuous camera angles. And basically what we did was we tried to simplify this as much as possible into just purely discrete action classes. And in order to do this, we ended up discretizing the camera actions. We discarded some combinations that would never be useful in the task. We discarded some actions that we found through our viewer that were never actually important for the task. And yeah, some other groupings to make sure that yeah, we were not like creating too many options that were not helpful. And then I'll also just briefly mention some things about our architecture and hyperparameters. In terms of hyperparams, our DQFD as well as the reward model, we mostly followed just the hyperparameters that were presented in the original papers without any tuning. And you'll see, so if you look at the diagram on the left, basically the main idea at a high level is just that we take the state in as, so on the left-hand side of this diagram, you have the state POV image, which we feed into a CNN. And then on the right-hand side, we have the other observations coming from the, for example, the inventory state and the equipment state. And those are basically just fed in into a final like linear layer. And then that architecture is used for the reward model as well as for the Q network. And then you can also just read off some of the training parameters that we have here for the DQFD training. And yeah. So it's, I think, also useful to mention some additional tricks we ended up using. So for example, we found that quite often we had situations where the agent was getting stuck, for example, where it ended up facing a corner or a wall, or it falls into a lake and it was just frozen there for a few seconds. We found that actually just keeping help the agent get nudged out of its stuck point. So that's one. And then the other one is that we actually, I think similarly to many other contestants, we struggled to make good progress on the village house and the animal pen tasks. So what we did is we ended up using this rather hacky approach where we used hard-coded actions, such as we'll place a stone block or place a fence or some other construction material with random probability as the agent is actually traversing through the environment. And this, yeah, you'll see this behavior in the videos coming after this. So just quickly, I'll show you some videos of our agent's performance. So here, what we're seeing is basically the agents performing in fine cave, and it's able to traverse the environment relatively effectively. It's able to climb the hill. Occasionally, it falls into a lake. But sometimes if it's good, then it's able to find its way out. And occasionally, if we're very lucky, not in this clip, but then we may find a cave. And then in the next task, here we're going to see the make waterfall task. Here you see the agent basically trying to jump up and climb up this hill. He gets stuck at a certain point. and then it decides here, hey, I'm just gonna create a waterfall right where I am. And you'll see that here it does result in a pretty nice waterfall with a nice backdrop, but unfortunately the agent just ignores that and runs past without taking the snapshot. So this is one thing that I think we commonly experience, that the agent was not actually doing the final snapshot for the waterfall. Okay. Then next, so here is where basically I was mentioning that for the animal pen task, we ended up encouraging the agent heavily to just place fences randomly as it was moving around. So you get this clearly pretty random behavior. And then you'll notice that the result of this is that the agent just traps itself inside a cage, unfortunately without any animals with it inside. So definitely a space where more research and work is needed. And so finally, I think we have a similar sort of outcome for the village house, where we also encourage this heavy-handed random placing of blocks. So you get this really abstract art pieces where the agent is building all kinds of different like doors, blocks, strange things. Yeah. So again, this is another area where I think much more work will be needed, and it would be interesting to see where research leads us in the future. All right. So I think with that comes to the end of the content I have. I just want to thank all my teammates and the organizers of the BASALT competition for this opportunity. I think we had a lot of fun and we learned a lot in the process. So thank you. And thank you for everyone here for listening to the presentation. We'll be happy to take any questions now.
Cool. Thank you so much. Yeah, does anyone have any questions?
I do.
Yes, Vinicius, go ahead.
So I didn't fully get how the auto labeler works. Can you just go over pretty quick about it, just like briefly?
Yeah, I can take this. Yeah, so the auto labeling is basically what we would do is we would, for each of these categories here, we would generate some trajectories. So for example, the demonstrations are provided. So we will sample a short clip from the demonstrations, and then we would, for example, run our model on some trajectory and sample a clip from that. And then this greater than sign is just saying that the clip sampled from human demonstrations, we will always label that as preferred over the clips that are generated by the model. And then a similar case is used for all of the other comparisons that we have here. Does that
reference in this auto labeler, like the frames that came from the human? Okay.
What's the difference between the late trajectory and versus early trajectory demos? Why? I didn't understand that.
So right, yeah. So this is basically resting on the assumption that for many of our tasks, and I should clarify that this is for human demonstrations. So the closer you are to the end of the trajectory, you're actually more likely to be close to completing the task, and so your reward should be higher. I can't remember the exact number, but it was something like the final clip sampled from the final 10% of a trajectory will be rated as preferred over clips sampled from an earlier part of the trajectory.
This is interesting. It's like, to me, learning from human preference is obviously a very powerful technique, and I like it a lot. But like, I think in where the environments that this type of work has been applied before, like maybe the tasks are shorter. On a longer task, if you're showing 2 clips, now you have this time component, right? You could have 2 really good clips, but they're in different parts of the task. Trying to rate which one is better, that's kind of a challenge, right?
Yeah, I do think that is one of the tricky things about this auto labeling, and it's likely one of the reasons that we did not actually get really great performance out from this reward model approach. Yeah, we would need to look more into that, like the pros and cons of this.
Yeah, I think it's also a problem even if you have human feedback, just because the trajectory so long compared to previous work. It's like, I don't know, several minutes of video.
Okay, any more questions? Can probably do one more question. Okay, I'll have a question then. What was my question? Oh yeah. So you mentioned that you didn't see any improvements from using the reward model. Did you see any changes? Did it become worse? Did it just become different in some way?
I think we would have to admit that I think we didn't really have that much time to do thorough evaluations. So we got the whole workflow working like a couple of days before the submission, and then we were seeing that it wasn't improving much. And in some cases, I think I saw that the behavior was changing like a bit for the worst. And then we decided, yeah, we would just like stop it here and then, yeah. And
Got it.
keep
That makes
what was
sense.
working. Yeah.
Cool.